It's Paul. You may think you have a snow day, but not quite, because here is the first half of today's Math 23 lecture. This is all devoted to numerical integration, and it's quite possible that almost all this material is familiar, that you saw it in your earlier calculus course, and all I'm doing is extending it in the obvious way from R to Rn. Many integrals that you want to evaluate cannot be done by using Fubini's theorem exactly, because the antiderivatives that you have to evaluate cannot be expressed in terms of elementary functions. And under those circumstances, we have to fall back on numerical methods. While upper and lower Riemann sums are wonderful theoretical tools, they're just about the worst imaginable tools for trying to get numerical estimates of integrals. And you're already familiar with some better rules from your previous course. You probably know the trapezoid rule, the midpoint rule, and you may even know Simpsons Rule. Let's consider an arbitrary rule for assigning a function value to a dyadic cube, and using that rule we'll call the resulting sum capital S sub n. In that case, if the function's integrable, then the limit of whatever Riemann sum rule you choose to use is equal to the value of the integral. I've tried to illustrate this in R. I'm using just 4 subdivisions. If I'm calculating the lower Riemann sum, I use the infimum in each subinterval, represented by a dotted line. To calculate the upper sum, I use the supremum, represented by solid lines. And for any other sum, call it capital S sub n, I'll use a value S sub c in each cube. And that cannot be smaller than the infimum. It cannot be larger than the supremum. I've represented it by dashed lines on the diagram. So, when we sum up the relevant quantities and multiply by the volume of each dyadic cube, we discover that the lower sum is less than or equal to S sub n, which in turn is less than or equal to the upper sum, U sub n. We're assuming that f is an integrable function, so as n goes to infinity, L sub n and U sub n approach a common limit. By the squeeze lemma, the sum S sub n is squeezed between those two and approaches the same limit. This reasoning applies in any number of dimensions and to any conceivable rule. A simple choice for a rule might be evaluate at the center of each dyadic cube. That's a generalization of the familiar midpoint rule. Another alternative would be evaluate at the center of each boundary face for the cube and use the numerical average of these values. That generalizes the trapezoid rule. A third rule is pick a point at random in each dyadic cube, evaluate there. That's known as a Monte Carlo approach, and it is actually quite good and quite standard for large numbers of dimensions. Now let's look at some rules that are exact for first-degree polynomials. I'm going to consider just integrating the identity function f of x equals x on the interval from 0 to h. And let's try this with the right Riemann sum. We evaluate the function at the right endpoint, where its value is h. We multiply by the width of the interval h, and we get an approximate value of the integral equal to h squared. If we use the left sum instead, then the value is 0 at the left endpoint, and our approximation to the integral is 0. Of course, the exact value is the integral of x from 0 to h, which is h squared over 2. So both the left sum and the right sum are wrong. in each case the magnitude of the error is h squared over 2. However, if I take the numerical average of the right sum and the left sum, I get h squared over 2, which agrees with the exact answer. That is a simple case of the trapezoid rule, which is exact for first-degree polynomials. There's another rule that's exact for first-degree polynomials. Sorry, I'm waiting for Big Ben to finish in the background. Well, I guess that timestamps this video as happening around 10 a.m. So if we evaluate halfway through the interval, f of h over 2 is h over 2. Multiply that by h, and we get h squared over 2, which is exactly the right answer. There really should be an exponent 2 here, but I'm working with software where I can't write that in. Sorry. Now, a fancier way of looking at this is both the trapezoid rule and the midpoint rule define linear functions from the space of polynomials whose degree is less than or equal to 1 to the real numbers. They're exact for the constant function f equals 1, and they're exact for the identity function f of x equals x, and therefore, by linearity, they're exact for any linear combination, any function of the form f of x equals mx plus b. We can't really formalize this sort of reasoning yet, though, because we need to extend our notion of vector space a bit. So far, all our vector spaces have been Rn or a subspace of Rn, and once we're done with our introduction to integration, we will go back and do a little more linear algebra, consider abstract vector spaces, consider in particular vector spaces whose elements are functions, and then we will be able to reason more carefully about these integration rules. The trapezoidal and midpoint rules are not exact on a quadratic polynomial. I'm going to consider just f of x equals x squared. But if we look at how they go wrong, we can guess a linear combination of them that is going to be exact. So let's try the trapezoidal rule on f of x equals x squared on the interval from 0 to h. The trapezoid rule says take 1/2 of the value at the left endpoint plus the value at the right endpoint. So we take 1/2 of 0 plus h squared, multiply by the width of the interval h, and get an approximation of 1/2 h cubed. That's the area of the triangle that is shown in the diagram. So that triangle is a special case of a trapezoid, and we've calculated its area. The exact answer is obtained by integrating the function x squared from 0 to h. We get 1/3 h cubed, and you can see the trapezoid result is a bit too large. It's too large by 1/6 h cubed. What about the midpoint rule? Well, the midpoint rule says evaluate in the middle of the interval, get the square of h over 2, multiply that by the width of the interval h, and you get the approximate value 1/4 h cubed. That's not very good either. Since the exact answer is 1/3 h cubed, we came up with something that's too small by 1/10, 12th h cubed. However, you may now have spotted a way to fix the situation. The trapezoid rule provides a result that's too large. The midpoint rule provides a result that's too small. If we combine them, we may be able to get those errors to cancel out. And since the error made by the trapezoid is twice as large in magnitude as the one made by the midpoint, all we have to do is use 2/3 midpoint and 1/3 trapezoid. This is known as Simpsons Rule, and it's already clear that's going to be exact on the second degree polynomial f of x equals x squared. This is the right way to remember Simpsons Rule. It's 2/3 midpoint plus 1/3 trapezoid, designed so that the errors cancel out on the polynomial x squared. Let's check our error. 2/3 midpoint means we've got 2/3 of the error minus 1/2 h cubed. 1/3 trapezoid gives us 1/3 of the error 1/6 h cubed, and when we combine those we get 0. The usual way of stating Simpsons Rule says in a single interval you use rates 1, 4, 1. The 4 comes from 2/3 midpoint. The 1 and 1 come from 1/3 trapezoid, which is split between the left endpoint and the right endpoint. So to apply Simpsons Rule in practice, you divide by the sum of the weights, which in this case is 6, and then you take a weighted average 1 times the value at the left endpoint 0 plus 4 times the value of x squared in the middle, which is h squared over 4, plus weight 1 times the value of x squared at the right endpoint, which is h squared. That gives us 1/6 of h squared plus h squared. We have to multiply by the width h of the interval, and we get 1/6 h cubed, which agrees with the exact value of the integral. Now there's a remarkable piece of serendipity. Simpsons Rule turns out also to be exact for cubic polynomials. And once we can deal with vector spaces of functions, we'll show that it's not exact not only for the specific cubic polynomial x cubed, but for an arbitrary cubic polynomial, and we'll be able to come up with a very simple proof of this fact. For the moment, I just want to show you this serendipitous result. If I integrate x cubed from 0 to h, I get, of course, 1/4 x fourth. If I use Simpsons Rule, I take 1/6 times 1 plus the value 0 at the left endpoint plus 4 times h over 2 cubed, which is the value in the middle, plus weight 1 times the value at the right endpoint, which is h cubed. I multiply by h. That gives me 1/6 of 1/2 h cubed plus h cubed, or 1/6 times 3/2 h cubed times h. That works out to 1/4 h to the 4th, which agrees with exact integration. Because of this fact, Simpsons Rule is perfect on cubic polynomials, and it's also amazingly good on polynomials that are on functions that are nicely approximated by cubic polynomials. Let me show you an example of this. First, let me state Simpsons Rule as an algorithm. Step 1. Forget everything you ever heard about dyadic cubes. Divide the interval of integration into little n equal subintervals. We don't want to use dyadic cubes because Simpsons Rule is a disaster when applied to discontinuous functions, and if a and b are not integers, or generally if they're not dyadic, the indicator function that we have to introduce will be discontinuous and mess up Simpsons Rule. So in this case, go back to doing what you used to do. Break up the interval from a to b into n equal subintervals. N does not have to be a power of 2. Evaluate the function at the endpoints of each of those intervals and also in the midpoint. So you're going to end up doing 2n plus 1 evaluations in all. And then calculate a weighted average of the function values, because after the first interval, every point that's an endpoint is both the right endpoint of one interval and the left endpoint of the next interval. It will give you a weight of 2. So the weight rule is 1, 4, 2, 4, 2, 4, ending up 2, 4, 1. And you end up dividing by the sum of all these weights, which is 6 times n. For the moment, forget about b and a. All you're computing is a weighted average of the function values. Once you've got a weighted average of the function values, multiply it by the length of the interval, because, in fact, the integral is the average times the length of the interval. So let's try this out on the function sine x. I'll integrate it from 0 to pi over 3 using Simpsons rule with n equals 1, which means 3 evaluation points. What's my weighted average? 1 over the sum of the weights times 1 times sine of 0 plus 4 times sine of pi over 6, that's the midpoint, plus 1 times the sine of pi over 3. Pi over 3 is the right endpoint. That's 1/6 of 0 plus 4 times a half plus 1 times root 3 over 2. It's 2 plus root 3 over 2 divided by 6. And then, to get the approximate value of the integral, I take that quantity and multiply by the length of the interval, which is pi over 3, getting 0.500216. A warning, it is awfully easy to forget to multiply by the length of the interval when you're using Simpsons rule. The average value that you get is not the integral. You have to multiply by b minus a. What's the exact answer? Well, I can integrate sine x from 0 to pi over 3 by elementary methods, and I get 1/2. Isn't that remarkably good? The approximation that we get by using just 3 evaluation points agrees in its first 3 decimal places with the exact answer. And if this sounds too good to be true, it really is. Simpsons rule is dandy for polynomial functions of degree up through 3, and by functions that are nicely approximated by such polynomial functions. The Taylor series for sine x, just up through terms in x cubed, is pretty good for x between 0 and pi over 3. But if you use a polynomial that has an x to the 4th term in it, if you use a function that has a discontinuity in it, Simpsons rule can be a terrible approximation, and in fact using a large number of subdivisions won't make matters much better if you've got a discontinuous function. We'll return to this issue after we have looked at vector spaces of functions. Let's try the same approach to get a numerical approximation to the natural logarithm of 2. The clever idea here is to notice that if you integrate dx over x from 4 to 8, you get the natural logarithm of 2, and this is very easy to do also by using Simpsons rule with n equals 2. n equals 2 means we have 2 times 2 plus 1, or 5 points of evaluation. So we'll do our weighted average. We're going to have to evaluate at 4, 5, 6, 7, and 8, and the weights by Simpsons rule are 1, 4, 2, 4, 1. Those sum to 12. So for our weighted average, we have 1/12 times the sum of 5 terms. We're evaluating 1 over x at 4, 5, 6, 7, and 8. 1 times a 4th plus a weight of 4 times a 5th plus a weight of 2 multiplied by 1/6 plus a weight of 4 times 1/7 plus finally a weight of 1 times 1/8. I actually added all these fractions together, Got 1747 over 840, multiplied that by 112, carefully remembered to multiply by the length of b minus a, 8 minus 4, and I got 0.69325. I can only remember 3 digits of the natural logarithm of 2, so I had to look it up. The exact value of the integral is 0.69315. So we're off by 1 in the 4th digit. If you do section problem 1b, you can use the same trick to evaluate the natural log of 3. But we want to do multivariable calculus. How can we extend this? Well, as long as we're integrating over a rectangle, there's an easy generalization. And if the function we're integrating happens to be a product of functions of individual variables, it becomes easier yet. In the textbook, this is stated for a function that's f1 of x1 times f2 of x2 on up through fn of xn. But it's easier to visualize what's going on when n is equal to 2, and the generalization to n is obvious. We're integrating f1, f2, dx1, dx2 over a rectangle, which is the Cartesian product of the interval AB for x1 and the interval CD for x2. And by a product rule that we proved in the first week of this course, we know that this integral can be evaluated by integrating f1 from a to b, integrating f2 from c to d, and multiplying the results together. Now, Simpsons rule, midpoint rule, trapezoid rule, whatever rule you use, gives an approximation of the form sum over I of the weight for point I times the function evaluated at point I. For the function of f2, we have a similar rule, only I'm going to use the subscript j. Then I can multiply these together, and we get a so-called product rule. It says the weight you need for evaluation at x equals pi, y equals pj is just wi times wj. Once you see an example, this formula will look pretty obvious. So let's try a product rule based on Simpsons rule. For integration over x, the weights are 1, 4, 1. For integration over y, the weights are also 1, 4, 1. And these weights wi sub wj are the circled numbers inside the square. Just the weight corresponding to x multiplied by the weight corresponding to y. That's why we get a 16 here. It's 4 times 4. Let's evaluate this, or let's test this by approximating the integral of x squared y cubed over a square where x and y both go from 0 to 2. The sum of the weights is 36. It has to be 6 times 6. And there are only 4 places where the function value is different from 0. Right smack in the middle, with a weight of 16 and x and y both equal to 1, we get 16 times the function value of 1. If we move to x equals 2, the weight is 4, and x squared is 4 in that case. If we move up here, where y equals 2, the weight is again 4, but the function value is 2 cubed, which is 8. And finally, up here, x and y are both equal to 2, so we get 32. When you look at this, it seems highly implausible that this would give you the right answer. Attaching any weight to this largest value, all these 0 values, putting so much weight on the value in the middle. But let's try it out. 4 over 36 is 1 over 9, and we end up adding 16, 16, 32, and 32, we get 96 over 9, or 32 over 3. It's easy to calculate the exact value for this function since it's a product of a function of x by a function of y, and when I do that evaluation, I get 32 over 3. In other words, evaluation at 9 points has given us exactly the right answer. Why did we get no error? The answer is this is a product of cubic polynomials in x and y, and Simpsons Rule is exact for cubic polynomials. If you do section problem 1a, you'll get a chance to use this approach for a function which is not a polynomial, namely sine of x plus y, but since it's nicely approximated by a sum of products of cubic polynomials, you will get remarkably good agreement with the correct answer. On the homework, as I recall, you'll actually get a chance to try out a generalization of this approach to 3 variables. That's all we're going to do with numerical integration for the moment. We'll return to this topic a little more theoretically after we have considered vector spaces of functions.